Welcome back. Um, welcome back to this lecture, chapter 10. Just making sure that the previous one is still converting over, so I can, record two at the same time. We'll see how this works. We just want to continue on with Lewis structures. We talked about Lewis structures working with ionic compounds. Now we're going to talk about Lewis structures working with covalent compounds, and this is really the power of the Lewis structure. Of Lewis structures. And so there are three different types of covalent bonds that we're going to talk about. There's single bonds, there's double bonds, and there are triple bonds. These bonds are formed by a pair of electrons known as a bonding pair of electrons, right? And these bonding pairs are usually found between two different elements. In this case, we have between a hydrogen and an oxygen. I will when we go through the steps with which to find the Lewis structure, we will talk about what this actually looks like. I have also posted on the Canvas site just some rules. The rules we're going to talk about are written out in a step-by-step way. You need to know the rules. You need to follow the rules. You need to do the rules. We need to practice, because if we don't, we can get very confused and our structures will not look the right way. And so two types of paired electrons. We have the bonding pair, and then whatever electron is not taking part in bonding is known as a lone pair, right? It's a lone. It's just chilling out in space. And so it is a lone pair. Now, one of the things that we can do, right, and we talked about, is that there can be more than one covalent bond, right? Double bonds form when more than one electron pair is shared. Commonly found in compounds containing oxygen, right? This is a key, right? Because oxygen has 6 to form an octet, they need 8. And so there is an ability to gain 2 electrons to form that double bond. Now, if you're thinking about, Dr. Bishop, how in the world am I supposed to know what forms a double bond and what doesn't? I'm glad you asked. We're going to talk about it. So here are the rules with which we need to learn before we can start making Lewis structures. So the number one rule is we need to write the correct skeletal structure for the model. And what I mean by that is we just need to put the molecular formula. We take the molecular formula, and actually 1 and 2, to be honest, are probably switched. I think your book presents it this way. In mine, I think I present it the other way. So whether you just, you take, and I'll show you, the molecular formula usually tells us how the chemical structure, the skeletal structure is supposed to be. But then we're supposed to calculate the total number of valence electrons, right? The valence electrons tell us how many electrons we have to do the chemistry from each individual molecule, or from each individual element in the molecule. And so we just need to count the electrons, right? It doesn't matter where they come from. It doesn't matter which atom that they have. We just care about that they have, all we care about is how many we have. And we need to then distribute the electrons among the atoms, giving octets or duets to as many atoms as possible. And then if any atoms lack an octet, we can then form double or triple bonds as necessary. So, and then we'll talk about how we can then further understand and maybe make our predictions a little bit better. But for now, we're just going to start here. So we're going to go to the board and we're going to look and see a way that we can do this. All right, let's go ahead. So if you remember, these are our Lewis dot structures, right? This is counting valence electrons. This will be very, very important for us when we start doing Lewis structures, that we can calculate valence electrons relatively quickly. So let's look at CO2. Right? So CO2. The way I normally do it is I just go ahead and calculate total amounts of electrons first, and then I make my skeletal structure. If you make a skeletal structure and then count, it doesn't matter. Those two things have to be done, though, before we can actually start making the model. Carbon, if we look, has 4 electrons. Oxygen has 6 valence electrons. Now, one oxygen has 6, so 2 oxygens is going to be 12 electrons, right? And so then all we do is we add this 4 plus this 12, and so now we have 16 total valence electrons to do chemistry. So what we said we were going to start doing is we're going to put carbon in the middle, right? And so how do I know we put carbon in the middle and these oxygens will go on the outside? Well, we know 2 reasons. One, and I'm going to present it in the next slide. One is we know that carbon's in the middle because it's known as the least electronegative atom, right? The least electronegative atom always goes in the middle. Usually always goes in the middle. That's one rule. That's one reason why we know carbon is in the atom. I'll tell you about electronegativity in a minute. Oxygen, or the other way we know, is that carbon is the beginning of the molecular formula. Usually. The exception is hydrogen. But usually, if whatever atom leads the molecular formula, that will be the atom in the center of the Lewis structure. And so now let's go ahead and let's start filling in electrons. Right? Let's start filling in electrons because we have 16 total electrons, right? Well, we know that there's going to be at least a bond, right, in between those two. There has to be a bonding pair between these two, right? And so we have now used 4 electrons. So we have 12 electrons left. Starting on the outside, we just fill in octets. Man, I'm glad we're done. Are we? Look at how many that carbon has. How many electrons does that carbon have? 1, 2, 3, 4. But what did we say that everything had to have for us to have a successful Lewis structure? That's right. Everything has to have an octet. And so we said that if everything is full and we've used up all our electrons, which we have, to where we can't put more electrons on the central atom, then what we need to do is we need to then think about forming double and triple bonds, right? And this is what we'll do, is we'll take this lone pair, or we'll take this pair of electrons and this pair of electrons, and we'll just move them in. And so now, because they're being shared, right? So oxygen gets these, carbon gets these. And what we see is now carbon has an octet, and these 2 oxygens still have their octet. And so this is the Lewis structure. There's another way we can draw this Lewis structure, and it just really depends on what you feel comfortable with and the way you see things. But we can also draw it like this, right? Where we replace those bonding pair of electrons with a line, right? And that both of these are equivalent. And just one lets you see the electrons, the other one doesn't necessarily. So I want you guys to practice this again on your own using the tricks. If you want to show me your work, if you want to send it to me, if you just want to show me in person, that'd be fine. I'll check it out. I want you to do these 2 compounds. Okay, so I want you to do NH3, and I want you to do H2CO. And again, just follow the rules, go step by step, and I am confident that you guys will be more than able to draw these Lewis structures. So let's go ahead, come back here. All right, so we talked about this. Not all covalent bonds are created equal, right? There is something known as polar covalent bonds. And what a polar covalent bond is, it is when one atom of the compound pulls the electron more to them than the other part of the compound. And so if we look, we describe it using what's known as electronegativity, right? One is more electronegative. One wants that electron more than the other, and it'll pull it. It's actually, I think there's a YouTube video called Chemistry with Dogs, and they do a great explanation on polar covalent bonds. And so I would recommend watching that and viewing that video. But what you can notice is that it's an intermediate type of bond, right? It's not exactly ionic bond to where those electrons are actually being ripped off right? And you're forming ions, but it's also not what's known as a pure covalent bond where it's shared equally. What we see is there's two ways to denote a polar covalent bond. One is with an arrow. Notice where that cross is. That cross is over the one that becomes more positive. And so that's where that cross is, and it's pointing towards the more electronegative, the one that will become slightly negative. You can also look at the gamma, right? We have gamma plus and gamma negative. So it's not a full positive charge, full negative charge, but it is a partial negative and partial positive charge. Water molecules have this. This is why water can climb up sides of glass. This is why water has a very high temperature to boil, right? Is because of these types of interactions. And so how do we know which one is which, or what's electronegative versus something else? And what we can see is it's another pattern in the periodic table. Starting with fluorine, right? Fluorine is the most electronegative element on the periodic table. And so obviously as you go up towards fluorine, you're going to become more electronegative. As you go away from fluorine, you become less electronegative. It's just like climbing a mountain, right? If you're on the peak, everywhere you go is going to go down. And so we can use electronegativity to describe the different types of bonds being formed. And now, if I were to ask you to ever calculate something like this, I would give you these numbers. But we should just be familiar that if there is a large enough difference in electronegativity, it will turn into an ionic compound. Let's look at the example of like lithium and fluorine, right? Lithium is 1, fluorine is 4, right? That is a change of 3. That means that fluorine is going to rip that electron away from the lithium, and they're going to form an ionic compound. Anything formed, so we looked at carbon and oxygen, right? The difference is 1, right? And so there is going to be an it's known as a polar. There's going to be a polar covalent bond. Now, what we're going to see is the shape will determine whether there is a slight positive and negative to the overall molecule. But for now, we're just looking at the bond itself. We'll look at that. Usually pure covalent bonds are those between the same element. So O2, Cl2, F2, things like that is where we'll find pure covalent bonds. We can quantify the polarity of a bond through the bond's what's known as a dipole moment. You won't have to calculate this, but I just want to show it to you just to show you that there are times in a molecule's life where it exhibits, again, a partial negative, partial positive. Some of them last longer than others. Some of them are a lot shorter than others. But I just want to show you that, depending on the distance and things like that, can change the dipole moment. You'll learn, I think, more about this in Gen Chem 2, and especially if you go further in chemistry into things like physical chemistry. So electrons can be shared, right? So usually when we draw covalent compounds, we draw them as static, right? That this is the way it looks. With CO2, this is the way it looks. What we're going to do is we're going to pause here just because the next few slides will take us some time to really go through. And I want to make sure that we have time to talk about resonance structures and formal charge, because usually when we talk, and then we'll have to calculate, again, another way to calculate delta H. Woo! But this way, we'll be able to spend some time doing that. But formal charge, we're going to talk about formal charge. We're going to talk about resonance. Usually when we talk about Lewis structures, gives students the biggest problem. And so I'd like to just take some time in part 3 to go over this.